Hello, welcome to a quick little tutorial on intermolecular forces. So one thing I would encourage you to do, please subscribe to my YouTube channel if you can down here. That'll kind of help. Here's some other good videos. Most importantly, if you look in the notes, you can download this and use this as guided notes, which I would really encourage you to do. This is about interparticle or intermolecular forces. We hope to go over what they are in general, the different types, such as ionic, metallic, dipole, hydrogen bonding, and van der Waals or London dispersion forces. So what are intermolecular forces? This is kind of a super important thing because it's generally saying interparticle or intermolecular forces are essentially there's something positive and something negative or pseudo-positive and pseudo-negative in each molecule that attracts the molecules to other molecules. This controls just about all physical properties, such as the states that they are, whether they're a solid, liquid, or gas, the boiling points, the melting points. Essentially, it's saying how much molecules want to stick to each other. It also can have an influence on chemical behaviors because if molecules don't mix together and can't touch, typically they don't react very well. We can't get bonds to break and form. So needless to say, this is a really important topic. Can we look at the symbolic and particular level and predict what's going to happen on a large scale? That's essentially what we're trying to do. So list of the forces are ionic metallic bonding, hydrogen bonding, which is a form of dipole. And then there's dipole, which we'll talk about. And then there's the nonpolar forces, such as van der Waals and London dispersion forces. Okay, so let's start with ionic. Basically, these are interparticle or intermolecular forces in which there's attractions between full positive and negative point charges, cations and anions. These are some of the strongest forces. These are really strong because they basically are saying, essentially, you've got a positive and a negative. And if you look, and we've talked about this a lot of times, but this negative here doesn't just attract to this positive, it attracts to this one, it attracts to this one, attracts to this one back here, and so do the positives. You got this. So that's why most ionic solids or ionic compounds usually are going to be solids at room temperature. They boil and melt at really high temperatures because there's very strong forces wanting to have those cling together. Next, we have metallic bonding. Now, there is bonding between metal atoms. Let me see if I can move this out of the way. But basically, for metallic bonding, you can think of these big nucleuses, okay, like these would, like think of like iron and these metals, magnesium, big nucleuses, and you have the sea of electrons, like a netting of these electrons, and they're d electrons, so they have room to kind of move around. And think of like a giant sea or netting of electrons that are like all over, sort of flowing around the positive nucleuses that are sort of stuck in the middle that kind of keeps them into place. That's why this ocean of electrons sort of keeps these nucleuses into place. And that's why most metals, generally speaking, tend to be solids at room temperature. There's only one that's a liquid. We never have gases, right? Because if this is stuck in a sea of millions of electrons, it can't just like pop out, right? So that would be an example of another interparticle force. Now, these are kind of interesting. These are called dipole. What if, and this gets into what we were talking about with Lewis dot structures. So you make a Lewis dot structure, you look at the different bonds. It's not symmetrical. One part of the Lewis dot structure can have an area that's very, that might be sort of negative, and the other part might have a place that's sort of positive. Not fully, but just because not symmetrical, the electronegativity, there could be polar bonds or ionic in character based on differences in electronegativity. That would allow an attractive force, which we call these are permanent dipoles. Okay, a great example of a permanent dipole, and you can sketch this out and do this real quick. HCl, otherwise known as hydrochloric acid. If we do the Lewis dot structure, it definitely has the H and the Cl is either it's like a In character, it would be polar or ionic in character, very close to that. Um, it is not symmetrical. It is a polar molecule. One side would definitely be somewhat negative. One side would definitely be somewhat positive. These would greatly attract to each other. Why is this important? Hey, don't forget, write this down. Likes dissolve likes, right? If you're working at a pool as a lifeguard and you have muriatic acid, which is basically concentrated HCl, and you're in a tiny shed, you open the top, those fumes are going to go right to the water vapor in your lungs or nasal passage. It will attract, it will dissolve, and your body will react very quickly, and it will not be positive, right? So, I mean, or not be a good thing. So, it's an attractive force. Likes dissolve likes. These dipoles and dipoles go together with any other dipoles, start reacting. So, there's an example of physical and chemical properties with that HCl. Next, hydrogen bonds. Okay, so this is actually now water is a beautiful case of a hydrogen bond. Think of hydrogen bonding materials are those that are permanent dipoles on steroids. However, here's the key, and people get this wrong every year. People always think, okay, the hydrogen bond means anything with hydrogen attached to some other atom. That's not what it means. You would think that would make sense. I get it. It should say hydrogen attractive forces. I don't know why they named this, but hydrogen bonding, it refers to when you have a hydrogen that's covalently bonded in a molecule, okay, that attracts to the oxygen, nitrogen, or fluorine atoms in another molecule. Now, let's look at this carefully. Here's water. The hydrogen bond they're talking about is not the H that's covalently bonded to the oxygen. That's not what they're talking about. It's saying, hey, this is a dipole. This is somewhat positive. This is somewhat negative. The hydrogen bonding is where this somewhat positive H attracts to the somewhat negative oxygen, or it could be nitrogen or fluorine, of another molecule. That's the hydrogen bonding attractive forces. Super important. If water did not hydrogen bond, we would not exist on this planet. If there were not hydrogen bonding with like nitrogen and hydrogen, DNA would not happen. Okay, we would not be alive. I mean, so this is really important. It's like dipole on steroids. Okay, it's really important. Again, oxygen, fluorine, or nitrogen on one atom goes with the hydrogen that is attracted to the other. So it's like this attractive force here. Super important. Next one. Let's go here. Okay, so now what if we don't have metals, we don't have ionic bonds, we don't have dipoles, permanent dipoles, no hydrogen bonding? What's left? Non-polar molecules, right? What happens is now there's a term called van der Waals and London dispersion forces. First of all, van der Waals says it's the sum of all of the forces attracted to all of the other forces. That's often confused with London dispersion forces. So we're going to primarily talk about London dispersion forces. London dispersion forces works like this. You have a non-polar molecule, and it goes to another non-polar molecule. And the electrons are evenly spread out. There's symmetry that cancels everything. Maybe you just have a bunch of non-polar bonds. One of the things that happens, could it be as one of these, okay, gets close to the other, the electrons are shifted for an instant to where you have a temporary dipole? That could happen. And that could create a force between those two molecules. And that indeed does happen. Now, does it happen often? Not too much. Is it a really strong force? No, not as much. Not as much. However, this is the thing you need to write down. Okay, so again, this is really important here. So nonpolar molecules have dipoles that are temporarily induced. Okay, but here's the important part. The larger the molecule is, the greater the odds that this can happen, and thus you have more of these forces. So when we make these molecules super big with lots of carbon chains and lots of hydrogen, you can actually have those as liquids and solids, even though they're very nonpolar. Plastic is a great example of this. Okay, styrofoam is a good example of this. There's even polypeptides in our bodies, a good example of it. Okay, so there you go. Again, and don't forget, likes dissolve likes. The goal now is to keep this framework and say, can we use this to predict what's going to happen on a large scale? That's what we're shooting for.